Hello everyone. Welcome to this lecture on programming good practices. Please take your seats and get comfortable because we're going to be here for quite some time. A very long time indeed. Before we begin, I want to take a moment to introduce myself. My name is Professor Henderson. I've been teaching programming for approximately 27 years now. Well, 27 years this coming March. Or is it February? Let me think about that for a moment. Yes, it was March. March of 1998 when I started. That's a long time ago. Things were different back then. Computers were different. Programming languages were different. But the fundamental principles of good programming have remained largely the same. Well, they've evolved somewhat, but the core ideas are still relevant today. Now, I should mention that my office hours are on Tuesdays and Thursdays from 2 to 4 in the afternoon. That's in room 307B. The B is important, not 307A, because that's Professor Mitchell's office, and he teaches database systems, which is a completely different subject. Although there is some overlap between our subjects, of course. There's always overlap in computer science, isn't there? Let me tell you a little joke before we dive into the material. Why do programmers prefer dark mode? Because light attracts bugs. You see, it's a double meaning. Bugs like insects are attracted to light. But bugs in software are errors, and programmers spend a lot of time dealing with those. So dark mode keeps the bugs away, supposedly. It's not a very good joke, I'll admit, but it's the kind of thing programmers find amusing. This session is going to cover programming good practices in considerable depth. Now, what exactly are good practices? That's an excellent question, and I'm glad I asked it. Good practices are essentially the established ways of doing things that have been found, through experience and collective wisdom, to produce better results than alternative approaches. They're practices that are good, as opposed to bad practices, which tend to lead to problems down the road. In programming, there are many different ways to accomplish the same task. You've probably heard the saying that there are many roads that lead to Rome. I've never actually been to Rome myself. I've been to Newark, which is in New Jersey, but not Rome. The saying holds true regardless. Some approaches to solving a problem are better than others. They lead to code that's easier to read, easier to maintain, and easier to modify when requirements change. Those are the good ways. Those are the practices we'll be discussing today. Before we get into the specifics, and we will get into specifics, I promise you, I want to establish some foundational concepts. Foundation is an important word here. Just like you can't build a house without a proper foundation, you can't write good software without understanding fundamental principles. Well, technically you could build a house without a foundation, but it wouldn't be a very good house. It would likely collapse or sink into the ground. Programming is similar in that respect. Let me outline what we're going to cover in this session. We have quite a bit of ground to cover. When I say quite a bit, I mean several hours worth of material. We'll be discussing naming conventions and how to name variables and functions appropriately. We'll talk about code comments and documentation. We'll examine function design principles. We'll explore the DRY principle, which stands for Don't Repeat Yourself. We'll discuss error handling and defensive programming. We'll look at code organization. We'll cover testing methodologies. We'll discuss version control, specifically Git. We'll talk about performance optimization, though I'll warn you now that premature optimization is often counterproductive. And we'll touch on security considerations. That's a lot of material, I know. But good programming practices encompass many different aspects of software development. It's not just about writing code that works. It's about writing code that can be maintained over time, code that other people can understand, and code that doesn't fall apart when unexpected situations occur. So now we arrive at the topic of naming conventions. Naming is the act of giving names to things, which is something humans have been doing for thousands of years. In programming, we name many things. We name variables, functions, classes, methods, parameters, constants, files, directories, packages, modules, and namespaces. So many things require names, and coming up with good names can actually be quite exhausting. Some people say that naming things is one of the two hard problems in computer science, the other being cache invalidation and off-by-one errors. That's actually a joke, because I just listed 3 things when I said there were 2, which is itself an off-by-one error. These are the kinds of jokes programmers tell each other at conferences. Let's start with variables. Variables are named storage locations in memory. You give them names, so you don't have to refer to them by their memory addresses, which would be something like 0x40201B8. Nobody wants to work with hexadecimal memory addresses. We used to do that back in the early days with assembly language and machine code, and it was tedious and error-prone. One wrong digit and your program would crash, or worse, it would do the wrong thing silently. That's why we have variable names. They provide abstraction and make code human-readable. Now, there are different conventions for naming variables, and different programming communities prefer different styles. Let me go through them systematically. First, we have camel case, which is spelled with a capital C and capital C. In camel case, the first word is lowercase and subsequent words have their first letter capitalized, like this is an example or my variable name or number of students. You can see the pattern with the capital letters creating humps, like the humps on a camel's back. It's quite visual when you think about it. This style is particularly popular in Java and JavaScript communities. Then we have Pascal case, which is named after the Pascal programming language, which itself was named after Blaise Pascal, the French mathematician from the 17th century. In Pascal case, every word starts with a capital letter, including the first word. So you'd have this as an example, or my class name, or a number of iterations. This is commonly used for class names in many object-oriented languages. Next is snake underscore case, which uses underscores to separate words, and everything is typically lowercase. So you'd have this underscore is underscore and underscore example, or my underscore variable underscore name, or number underscore of underscore records. This style is very popular in Python and Ruby communities. The underscores sit low like a snake on the ground, which is where the name comes from. It's quite descriptive, really. There's also kebab case, which uses hyphens instead of underscores, like this is an example. However, this is less common for variable names because many programming languages interpret the hyphen as a minus sign, creating ambiguity. Is this variable name a variable name, or is it this minus variable minus name? The parser can't tell, so most languages don't allow hyphens and identifiers. Different style guides and different organizations have different preferences. Some require snake underscore case, some require camel case, some allow developers to choose. The important thing is consistency within a project. If your team has decided to use camel case for variables, then everyone should use camel case for variables. Mixing styles makes the code base look inconsistent and unprofessional. Now let's talk about what makes a good variable name, beyond just a capitalization style. A good variable name should be descriptive. It should tell you what the variable contains or represents. If you have a variable that stores the number of items in a shopping cart, calling it number of items or item count is much better than calling it an, or x, or temp. Single-letter variable names are acceptable in very limited contexts, like loop counters where I and j are conventional, or in mathematical formulas where the variable names match the mathematical notation. But in general, you want names that communicate meaning. The length of a variable name should be appropriate to its scope and importance. A loop counter that exists for 3 lines can be called I without issue. A variable that's used throughout a large function should have a more descriptive name. A variable that's part of a class's public interface and will be used by code throughout your application should have a very clear, unambiguous name. The broader the scope, the more important it is to have a descriptive name. Boolean variables deserve special mention. A Boolean is a variable that can only be true or false, yes or no. Good names for Boolean variables often start with is or has, or can, or should. For example, is valid, has children, can delete, should retry. When you read these names, it's immediately clear that they're Booleans and what they represent. Compare that to Boolean named status or flag, which tells you very little about what the variable actually means. Constants should be named differently from regular variables in many programming languages. The convention in languages like Java and C is to use all underscore caps underscore with underscore underscores for constants. So you might have max underscore try underscore count or default underscore timeout underscore seconds. This makes it immediately obvious when you're looking at a constant value rather than a regular variable. Other languages like Python use the same convention, though it's not enforced by the language itself, just by community convention. Function and method names also follow conventions. They typically use verbs or verb phrases, because functions do things. Calculate tax, send email, validate input, get user data. The name should describe what the function does. If you find it difficult to name a function because it does multiple unrelated things, that's often a sign that the function should be split up into smaller, more focused functions. Abbreviations and names are a contentious topic. Some people avoid them entirely, preferring to spell everything out. Others use common abbreviations to keep names shorter. My personal view is that well-known abbreviations are fine. Using HTTP instead of spelling out Hypertext Transfer Protocol is perfectly reasonable. Using number for number is common enough that most people will understand it, but using obscure abbreviations that only you understand is problematic. If someone else has to look up what PNSMFL means, your variable name has failed its purpose. Context also matters when naming things. If you're in a function called process user registration, you don't need to prefix every variable with user because it's already clear from context that you're dealing with user-related data. A variable called email is sufficient. You don't need user email in that context. But if you're in a more general context where you're dealing with multiple types of entities, then yes, user email might be appropriate to distinguish it from company email or other similar concepts. Magic numbers deserve special mention here as well. A magic number is a literal value that appears in code without explanation. If you see, if count greater than 42 in code, what does 42 represent? Nobody knows. It's magic. It appeared mysteriously with no explanation. The solution is to give it a name. Define a constant called max_items_pr_page or answer_to_life_universe_and_everything, and then use that constant instead of the literal number. Now the meaning is clear. Now we move to the subject of code comments and documentation. Comments are written explanations within your code that are intended for humans, not for computers. The computer completely ignores comments when it compiles or interprets your code. They're purely for the benefit of people who read the code later, which includes future you, your coworkers, and anyone else who might maintain this code in the future. Comments are annotations that explain what the code does, why it does it, how it does it, or sometimes when it should do it. They answer questions that the code itself might not make obvious. The code shows you what is happening mechanically, but it doesn't always explain the reasoning behind it. That's where comments come in. Why did you choose this particular algorithm? Why did you implement this workaround? Why is this value set to 17 specifically? These are the kinds of things that comments should explain. Let me tell you a joke before we continue. Why do programmers always mix up Halloween and Christmas? Because October 31st equals December 25. You see, in octal notation, which is base 8, 31 equals 25 in decimal notation, which is base 10. So October 31 equals dec 25. It's a play on the abbreviations for October and octal, December and decimal. I realize I've told this joke before, earlier in this lecture. That's what happens in long presentations. You start repeating yourself occasionally. My apologies for that. Different programming languages have different syntax for comments. In many languages, 2 forward slashes create a single-line comment. Everything after those slashes, until the end of that line, is treated as a comment. Then on the next line, you're back to regular code. 4 multi-line comments, also called block comments. Many languages use /* to begin and */ to end the comment. Everything between those markers is considered a comment, regardless of how many lines it spans. Now let's discuss what you should comment and what you shouldn't comment. This is actually quite important and often misunderstood. The first rule is, don't comment the what, comment the why. The code itself shows what it's doing. If you have a line that says I equals I plus 1, you don't need a comment that says increment I. That's redundant and adds no value. In fact, it makes the code harder to read because there's more text to parse through without any additional information. What you should comment is the reasoning behind decisions. Why are you incrementing I at this particular point? Why are you using this specific algorithm instead of a simpler one? Why is there this strange workaround that looks unnecessarily complicated? These are the things that future readers will want to know. 6 months from now, when you've forgotten the context, or when someone else is maintaining your code, they'll look at that complicated section and wonder why it's written that way. A good comment explains the reasoning. If your code requires extensive comments to explain what it's doing, that's often a sign that the code itself should be rewritten to be clearer. Well-written code is self-documenting to a large extent. If you use good variable names, if you break complex operations into well-named functions, if you structure your logic clearly, then much of the code becomes understandable without comments. This is an ideal that we strive for, though it's not always fully achievable in practice. There are, however, situations where comments are absolutely necessary. Complex algorithms, especially ones taken from academic papers or textbooks, benefit greatly from comments explaining what's happening. Business logic that implements complicated rules or regulations should be commented. Workarounds for bugs in third-party libraries or frameworks should definitely be commented, explaining what the bug is and why this workaround is necessary. Performance-critical code, where you've made non-obvious optimizations, should be commented to explain what you optimized and why. Documentation comments are a special category. These are comments that describe the interface of a function or class in a structured way that tools can extract to generate documentation. In Java, these are called Java comments. In Python, they're called docstrings. In JavaScript, you might use JSDoc. These follow specific formats with tags for parameters, returned values, exceptions, and other metadata. These documentation comments are very valuable because they can be automatically processed to create formatted documentation for your API. One common problem with comments is that they become stale. Code changes, but comments don't get updated. Now you have comments that say one thing, while the code does something else. This is worse than having no comments at all because it's actively misleading. When you modify code, you must also update any comments that relate to that code. This is one reason to minimize comments. The fewer comments you have, the fewer comments you need to maintain. Another issue is commented out code. Sometimes developers comment out sections of code instead of deleting them, thinking they might need that code later. This is a bad practice. It clutters your code base with dead code that nobody knows whether it's still relevant. If you need old code, that's what version control is for. You can always look back at previous versions if you need to see how something used to work. Don't leave commented out code in your active code base. To-do comments are worth discussing. These are comments that mark places where something needs to be done later. They're useful for marking work in progress or for noting future improvements. However, to-do comments can accumulate and become a form of technical debt. It's easy to add a to-do with the intention of addressing it soon, and then never actually get around to it. 3 years later, someone finds a to-do from 2015 and has no idea whether it's still relevant or what it was referring to. If you use to-do comments, you should have a process for reviewing them regularly and either addressing them or removing them. Some teams use special comment markers that can be searched. In addition to to-do, you might see fixem for things that are broken and need fixing, hack for code that works but isn't a proper solution, or note for important information that doesn't fit in the other categories. These markers make it easy to search your entire codebase and find all the places that need attention. However, like to-do comments, these need to be managed and not allowed to accumulate indefinitely. Header comments at the top of files are common in some codebases. These might include copyright information, license information, a description of what the file contains, or metadata about who wrote it and when. Whether you need these depends on your project and organization. Some open-source licenses require copyright notices in every file. Some companies have policies requiring certain header information. In other cases, they're optional and perhaps unnecessary, given that version control systems already track authorship and modification history. The key principle with comments is that they should add value. If a comment doesn't tell the reader something they couldn't figure out from reading the code, it's probably not necessary. Let us now turn our attention to functions and methods. Functions and methods are essentially the same thing. Though the terminology varies, depending on whether you're working in a procedural or object-oriented context. In object-oriented languages, methods are functions that belong to objects or classes. They're member functions, bound to instances. In procedural languages, you just have functions, which are freestanding entities not attached to any particular object. The concepts are similar enough that I'll mostly use the term function to refer to both, unless the distinction is important. Now, before we delve into the specifics of function design, let me share a small joke with you. Why do programmers prefer functions over relationships? Because functions have clear inputs and outputs, while relationships are much more complicated and unpredictable. That's programming humor for you. Functions are deterministic. You give them the same inputs, they give you the same outputs, every single time. They're consistent, reliable, and predictable. Relationships between people, on the other hand, are none of those things. But we're not here to discuss human relationships. We're here to discuss functions. Functions should do one thing. This is the single responsibility principle, which is one of the solid principles of object-oriented design. SOLID is an acronym standing for single responsibility, open-closed, Liskov substitution, interface segregation, and dependency inversion. These were popularized by Robert Martin, who's often called Uncle Bob in the programming community. He's written extensively about clean code and software craftsmanship. The single responsibility principle states that a function should have one reason to change, one responsibility, one purpose. It should do that one thing well and not try to do multiple unrelated things. But what does one thing actually mean? That's a reasonable question, and the answer is somewhat contextual. It depends on the level of abstraction you're working at. At a high level, a function called process customer order might be doing one thing, which is processing an order. But if you look more closely, that involves multiple steps. It validates the order, checks inventory, calculates the total, processes payment, updates the database, and sends a confirmation email. So is it doing one thing or six things? The answer is that it depends on your perspective and the level of abstraction. The key is that all the statements in a function should be at approximately the same level of abstraction. If you're writing high-level coordinating code, all your statements should be high-level operations like validate order and process payment. You shouldn't mix high-level abstract operations with low-level details, like parsing strings or manipulating bits. Those low-level details should be hidden away in their own lower-level functions. This creates a hierarchical structure where each level of functions operates at a consistent level of abstraction. Now let's discuss function length. How long should a function be? The general answer is short. But how short is short? Robert Martin has suggested that functions should ideally be 3 to 5 lines long. That seems extraordinarily short, almost impossibly short. And indeed, most functions you'll encounter in real code bases are longer than that. But the principle is sound. Shorter functions are better than longer functions, all else being equal. Why are shorter functions better? There are several reasons. First, short functions are easier to understand. You can see the entire function on your screen at once without scrolling. You can comprehend what it does in a single glance. Long functions require scrolling up and down. By the time you reach the end, you've forgotten what happened at the beginning. You have to keep more information in your working memory, and human working memory is quite limited. Studies have shown that we can typically hold about 7 items in working memory, plus or minus 2. A function that's too long exceeds that capacity. Second, short functions are easier to test. A short function with a clear single purpose is straightforward to test. You can easily write test cases that exercise all the code paths. A long function with multiple responsibilities and many branches becomes combinatorially complex. The number of possible code paths explodes. You can't practically test all of them. You have to sample and hope you've covered the important cases. Third, short functions are more likely to be reusable. A function that does one specific thing might be useful in multiple places. A long function that does many things is unlikely to be exactly what you need somewhere else. If your function is short and focused, you can call it from various places. This promotes code reuse and helps you follow the dry principle, which we discussed in an earlier section. Fourth, short functions are easier to name. When a function does one clear thing, You can give it a clear, descriptive name that accurately reflects what it does. When a function does many things, what do you call it? You end up with vague names like process data or handle request, which don't really tell you anything specific. A well-named function serves as documentation. You can read the function name and understand what it does without having to read the implementation. So, how do you keep functions short? The primary technique is extraction. If your function is getting long, you look for logical chunks of code that belong together and extract them into their own functions. You replace that chunk with a function call. Your original function becomes shorter and more abstract. The extracted function contains the details. This process of continuously extracting functions creates a hierarchical structure where high-level functions call lower-level functions, which in turn call even lower-level functions. Some people worry that this creates too many functions and makes the code harder to navigate. There's some truth to this concern. If you have hundreds of tiny functions, finding the one you want can be challenging. Good naming helps with this. Good organization helps with this. Good IDE support helps with this. Modern development environments make it easy to jump to function definitions and to search for functions by name. The benefits of small functions generally outweigh the navigation challenges. Let's talk about function parameters. How many parameters should a function have? The ideal number is 0. A function with no parameters is simple to call and simple to understand. You don't need to remember what to pass or in what order. However, 0 parameters is often not practical. Functions usually need input data to work with. So the next best thing is 1 parameter. 1 input, 1 thing to pass, simple and clean. 2 parameters is still manageable. Most people can easily remember what 2 parameters are and what order they go in, especially if the function is well named. 3 parameters starts to get tricky. Now you have to remember 3 things and their order. If you're calling this function in multiple places, you might make mistakes about the order. 4 or more parameters is generally too many. At that point, you should consider creating a parameter object. Group related parameters together into a structure or class, and pass that object instead. Now you have 1 parameter again, an object, which contains multiple fields. Why do fewer parameters matter? Several reasons. First, functions with fewer parameters are easier to understand and easier to call. You don't have to remember as much. Second, they're easier to test. If you have Boolean parameters, each one doubles the number of test cases you need. 2 Boolean parameters means 4 combinations to test. 3 Boolean parameters means 8 combinations. 4 means 16. The testing complexity grows exponentially with the number of parameters. Third, fewer parameters mean looser coupling. Every parameter is a dependency. The function depends on receiving that data. The caller must provide that data. This creates coupling between the function and its callers. Reducing parameters reduces coupling. Of course, sometimes you genuinely need multiple pieces of information, and there's no avoiding that. But often, when a function needs many parameters, it's a sign that the function is trying to do too much or that your abstraction boundaries aren't quite right. There are several techniques for reducing parameter counts. If your function is a method in a class, you can use instance variables instead of parameters. Store the data in the object, and the method can access it directly. This works when the data truly belongs to the object and represents part of its state. Another technique is to pass objects instead of primitive values. Instead of passing first name, last name, email, and phone number as 4 separate parameters, pass a user object that contains all of those fields. This is called the parameter object pattern. For functions that need many parameters, especially optional parameters, the builder pattern can be useful. Instead of calling the function with a long list of parameters, you create a builder object, set the parameters on it one at a time with method calls, and then call a build or execute method to actually perform the operation. This makes the code more readable because each parameter is explicitly named at the call site. It also handles optional parameters elegantly. You only set the ones you need. Now let's discuss function return values. What should a function return? That depends on what the function does. If it calculates something, it should return the result. If it queries something, it should return the data. If it performs an action, it might return nothing, or it might return a status indicating success or failure. Different approaches are appropriate in different contexts. Some functions return a Boolean indicating success or failure. This is simple but limited. It tells you whether the operation worked, but not why it failed if it didn't work. Other functions return an error code, an integer where 0 means success, and various non-zero values indicate different types of failures. This provides more information but requires the caller to know what the different error codes mean. Some languages and paradigms prefer exceptions for signaling errors. The function either succeeds and returns normally, or it fails and throws an exception that propagates up the call stack until something catches it. More recently, some languages have adopted result types. A result is a container that either holds a successful value or holds an error. The type system forces you to check which one you got before you can access the value. This provides compile time safety and makes error handling explicit. Each approach has trade-offs. Error codes are explicit but verbose. Exceptions are convenient but create hidden control flow. Result types are safe but require more ceremony. Functions should generally avoid side effects when possible. A side effect is when a function modifies something outside of itself, like changing a global variable, modifying a parameter object, writing to a file, or updating a database. Functions without side effects are called pure functions. They only depend on their parameters, and they only affect the world through their return value. Pure functions are easier to understand, easier to test, and easier to reason about. They're also easier to parallelize because they don't have hidden dependencies. Of course, programs need to have side effects eventually. That's how they interact with the world. A program that never writes to files or updates databases or displays things on screen isn't very useful. But you can minimize side effects and isolate them to specific parts of your codebase. Keep your core logic pure and push the side effects to the edges. This makes your core logic easier to work with. Function composition is a powerful concept. Small functions that each do one thing can be combined to create more complex behavior. This is similar to how Unix command line tools work. Each tool does one thing well, and you pipe them together to accomplish complex tasks. Well-designed functions can be composed in similar ways. The output of one function becomes the input to another. Building complex systems from simple, composable pieces is a fundamental technique in software design. Let me tell you another joke. What do you call a function that doesn't return anything? A void function. That's not really a joke, is it? It's just the actual terminology. But I presented it as if it were a joke, which is itself a sort of meta-joke. Programming humor is often quite self-referential and requires you to think about the structure of the joke itself. Or perhaps I'm just not very good at telling jokes, which is equally possible. In summary, good function design is about doing one thing well, keeping functions short, minimizing parameters, being clear about return values and error handling, and avoiding unnecessary side effects. These principles work together to create code that's easier to understand, easier to test, easier to maintain, and easier to modify when requirements change. And requirements always change. That's one of the few certainties in software development. Now we arrive at the DRY principle. DRY stands for don't repeat yourself. It's one of the most fundamental principles in programming, and yet it's also one of the most frequently violated. The principle is simple to state. Every piece of knowledge or logic should exist in exactly one place in your codebase. Don't duplicate code. Don't duplicate data. Don't duplicate logic. Write it once and reference it from wherever you need it. Why is duplication bad? Let me explain in detail, because this is important. When you duplicate code, you create a maintenance burden. Imagine you have the same code in two different places. At first, this seems harmless. Both copies work fine. But then requirements change, and they always change. You need to modify the behavior that this code implements. Now you have to modify it in two places. Do you remember that there are two places? Maybe. Probably not, especially if some time has passed. You modify one copy and forget about the other. Now your code base has inconsistent behavior. One place has the new logic, the other has the old logic. Which one gets called depends on the code path, on user input, on circumstances that might not be obvious. This leads to bugs that are difficult to diagnose and difficult to fix. Let me tell you a joke. Why do programmers always confuse Halloween and Christmas? Because October 31st equals December 25. I've told this joke before, haven't I? Earlier in this lecture. I'm repeating myself. I'm violating the dry principle in this very lecture about not repeating yourself. There's a certain irony in that. Or perhaps it's a meta-demonstration of the problem. When you repeat yourself, you create inconsistency. I might tell the joke slightly differently each time. The details might drift. People who heard it the first time might be annoyed hearing it again. This is exactly what happens with duplicated code. The dry principle applies to more than just code. It applies to data as well. If you store the same piece of information in multiple places, you have to keep those places synchronized. If a customer's email address is stored in 3 different database tables, what happens when the customer changes their email address? You have to update all 3 tables. If you miss one, your data is inconsistent. Some parts of your system will have the new email, others will have the old email. This causes problems. Messages go to the wrong address. Users can't log in. Reports show conflicting information. Configuration is another area where duplication causes problems. If you have the same configuration value hard-coded in 10 different files, changing that value requires finding and updating all 10 files. You might miss some. You might update them inconsistently. The solution is to have one authoritative source for configuration, and everything else references that source. Change it once, and the change propagates everywhere automatically. There are different types of duplication, and they require different solutions. The most obvious type is literal duplication, where you have exactly the same code in multiple places. Maybe you copied and pasted a block of code. Maybe you wrote similar code in 2 different places without realizing they were the same. This type of duplication is the easiest to fix. You extract the duplicated code into a function, and you call that function from both places. Now the logic exists in one place, and both code paths use it. Another type is structural duplication, where the code isn't exactly the same, but follows the same pattern. The structure is the same, but the details differ. Maybe you have 2 functions that both loop through a list, perform some operation on each item, and collect the results. The operations are different, but the structure is identical. This type of duplication can be addressed by extracting the common structure and parameterizing the differences. You create a function that takes the varying part as a parameter, often as a function itself. This is a common pattern in functional programming. Semantic duplication is subtler. This is when you have 2 pieces of code that do the same thing, but are implemented differently. Maybe 2 different developers, working at different times, implemented the same functionality without knowing the other had already done it. Now you have 2 implementations of the same concept. They might have subtle differences. They might have bugs in different places. Users might encounter different behavior, depending on which code path they hit. This type of duplication is harder to find and harder to fix, but it's important to eliminate it when you discover it. Documentation can also have duplication problems. If the same information is written in multiple documents, those documents can drift out of sync. One gets updated, others don't. Now you have conflicting documentation, and users don't know which to trust. The solution is to have one authoritative source for each piece of information, and other documents reference or link to that source, rather than duplicating the content. However, I need to mention an important caveat. Not all repetition is duplication. Sometimes code looks similar, but actually represents different concepts that happen to look alike coincidentally. If you have 2 functions that look similar but serve different purposes, and would change for different reasons, they should stay separate. Trying to combine them into one function would create inappropriate coupling. This is sometimes called accidental similarity or coincidental duplication. There's a rule of thumb called the rule of 3. When you see something once, that's fine. When you see it a second time, take note. When you see it a third time, now you refactor and remove the duplication. The idea is that you need to see a pattern repeated several times before you can be confident that it's truly a pattern worth abstracting, rather than just a coincidence. This helps you avoid premature abstraction, which can be worse than duplication. Premature abstraction is when you try to eliminate duplication before you really understand the pattern. You create an abstraction that seems right based on 2 similar pieces of code, but then later you discover they're not as similar as you thought. They need to diverge in ways your abstraction doesn't accommodate. Now you have to either break the abstraction, which means duplicating again, or you have to make the abstraction more complex to handle both cases. Both options are painful. Sometimes it's better to tolerate a bit of duplication until you're certain you understand the underlying pattern. Functions are the most common tool for eliminating duplication, but they're not the only tool. Classes and objects can encapsulate both data and behavior, eliminating duplication at a higher level. Inheritance allows child classes to share behavior from parent classes, though inheritance should be used carefully because it creates strong coupling. Composition, where objects contain other objects and delegate to them, is often a better choice than inheritance. Design patterns are essentially named solutions to common problems, and many of them are about eliminating duplication in sophisticated ways. The strategy pattern lets you encapsulate different algorithms and swap them out, eliminating duplication of the code that uses those algorithms. The template method pattern defines a skeleton of an algorithm in a base class, with subclasses filling in the details, eliminating duplication of the overall structure. The decorator pattern lets you add responsibilities to objects dynamically, eliminating duplication of enhancement code. Higher-order functions, which are functions that take other functions as parameters or return functions as results, are powerful tools for eliminating duplication. If you have several functions that all follow the same pattern but differ in one specific operation, you can extract that pattern into a higher-order function that takes the varying operation as a parameter. This is common in functional programming and is becoming more common in other paradigms as well. Code generation and metaprogramming are advanced techniques for eliminating duplication. If you need to write a lot of similar boilerplate code, you can write a program that generates that code for you. The generation logic exists in one place, and it produces all the similar code automatically. Changes to the generation logic automatically propagate to all the generated code. This is particularly useful for things like object relational mapping, serialization, and protocol handling, where you need similar code for many different data structures. Configuration-driven behavior is another approach. Instead of hard-coding behavior in multiple places, you externalize it into configuration. The code that interprets the configuration exists once, and the configuration can vary without changing code. This is common in systems that need to behave differently in different deployments or for different customers. The core logic is the same, but the configuration drives the specific behavior. Database normalization is the data equivalent of the dry principle. In a normalized database, each fact is stored in exactly one place. Other tables reference that fact through foreign keys, rather than duplicating it. This eliminates update anomalies and ensures consistency. Denormalization, where you deliberately duplicate data for performance reasons, should be done carefully and only when necessary, because it reintroduces all the problems of duplication. Testing code should also follow the dry principle. If you find yourself writing very similar test cases over and over, with only minor variations, that's a form of duplication. You can extract the common setup and assertion logic into helper functions or parameterized tests. This makes your tests more maintainable and ensures they stay consistent as the code under test evolves. The dry principle extends beyond code to the entire software development process. Don't duplicate requirements in multiple documents. Don't duplicate information between documentation and code. Don't duplicate knowledge across team members without sharing it. The principle is fundamentally about having a single source of truth for everything. When something needs to change, there's one obvious place to change it, and that change automatically propagates to everywhere that depends on it. However, applying dry requires judgment. Over-aggressive deduplication can make code harder to understand by creating excessive abstraction. If you have to jump through 5 levels of indirection to understand what a simple piece of code does, you've probably gone too far. The goal is to eliminate meaningful duplication while keeping the code understandable and maintainable. This balance comes with experience. As you work with code over time, you develop intuition for when abstraction helps and when it hurts. In practice, achieving perfect dry is impossible and probably not even desirable. Some amount of repetition is acceptable and even beneficial if it makes the code clearer. The principle is a guideline, Not an absolute rule, but it's an important guideline. Duplication is one of the primary sources of technical debt and maintenance burden in software systems. Being aware of it, actively looking for it, and thoughtfully eliminating it when you find it will significantly improve the quality and maintainability of your code. We now turn to the subject of error handling and defensive programming. Error handling is one of those topics that sounds rather straightforward when you first encounter it, but becomes increasingly complex the more you think about it. And believe me, I've thought about it quite a lot over the years. 27 years of teaching gives you plenty of time to contemplate these things. So what is error handling? Well, in the simplest terms, it's what your program does when something goes wrong. And things will go wrong. They always do. Murphy's Law states that anything that can go wrong will go wrong. I mentioned this earlier in the lecture, but it's worth repeating because it's such a fundamental truth in programming. Your code will encounter unexpected situations. Users will provide invalid input. Networks will fail at the worst possible moment. Databases will become temporarily unavailable. Files will be missing or corrupted. This is simply the reality of software development. Defensive programming is the practice of writing code that anticipates these problems. It's about being pessimistic in a productive way. You assume that things will go wrong, and you prepare for those eventualities. Some people call this paranoid programming, and honestly, that's not entirely inaccurate. A healthy dose of paranoia is quite valuable in software development. You need to think about all the ways things could fail and plan for them. Let me tell you a joke before we go further. What's the difference between a bug and a feature? Documentation. If it's documented, it's a feature. If it's not documented, it's a bug. That's programmer humor for you. Cynical, perhaps, but based on an uncomfortable amount of truth. Sometimes bugs do become features because users start depending on them, and fixing them would break existing workflows. It's not ideal, but happens more often than we'd like to admit. Now, error handling begins with validation. Input validation, specifically. And here's the first rule you need to remember. Never trust input. Never. I don't care where it's coming from. User input, file input, network input, database input, even input from other parts of your own system. Validate it. Check it. Verify it. This is not optional. This is mandatory. Why is this so important? Well, users make mistakes. They type the wrong things. They misunderstand your interface. They try creative things you never anticipated. And sometimes, though rarely, they're actively trying to break your system. SQL injection attacks, cross-site scripting, buffer overflows. These are all examples of what can happen when you trust input that you shouldn't trust. These aren't theoretical concerns. These are real vulnerabilities that lead to real security breaches that cost companies real money and damage real reputations. What does validation actually mean? It means checking that the data meets your expectations. Is it the right type? Is it in the expected range? Does it match the expected format? Is it the right length? Does it satisfy all the constraints your system requires? If the answer to any of these questions is no, then you reject the input. You don't process it. You don't store it. You don't use it. You return an error. You log a warning. You display a message to the user, but you absolutely do not proceed with invalid data. There's an old saying in computer science, garbage in, garbage out. If you accept invalid input, you'll produce invalid output. And that's the best case scenario. The worst case is that you'll introduce security vulnerabilities, corrupt your database, crash your system, or cause financial losses. I'm not being dramatic here. These things actually happen, and they happen because someone, somewhere, didn't validate their inputs properly. Let's discuss the different categories of errors you'll encounter. I like to think of them in three main groups, though other people might categorize them differently. Everyone has their own taxonomy, their own way of organizing these concepts. But these three categories have served me well over the years. The first category is programmer errors. These are bugs, mistakes in the code itself, logic errors, syntax errors, type errors. In an ideal world, these wouldn't exist. In an ideal development process, with perfect testing and perfect code review, we'd catch all of these before they reached production. But we don't live in an ideal world, do we? We're human beings. We make mistakes. We misunderstand requirements. We misread API documentation. We make incorrect assumptions. We have lapses in attention. We get tired and make silly mistakes late in the day. It happens to everyone, regardless of experience level. The second category is operational errors. These are runtime errors that occur because of environmental conditions. A file doesn't exist. A network connection times out. A database becomes temporarily unavailable. The disk fills up. Memory gets exhausted. These aren't bugs in your code exactly, though you could argue that failing to handle them properly is a bug. These are expected problems in the sense that you should expect them to eventually happen. Not if, but when. A robust system needs to handle these gracefully. The third category is user errors. Invalid input, incorrect data, misunderstanding the interface. Users click the wrong button, enter the wrong value, upload the wrong file. This happens constantly, and it's not because users are stupid. They're not. They're just not programmers. They don't think the way we think. They don't understand the constraints and requirements we've built into our systems. They're exploring, trying things, seeing what happens. This is normal human behavior, and our systems need to accommodate it. Now let's talk about the actual mechanisms for handling errors. Different programming languages take very different approaches to this problem, and each approach has its advantages and disadvantages. There's no universally correct answer here, which is frustrating for those of us who like clear, definitive rules. The traditional approach, used extensively in C and other older languages, is return codes. A function returns an integer value, where 0 indicates success, and non-zero values indicate various types of failures. Different error codes mean different things. The caller is responsible for checking this return value and handling errors appropriately. The problem with this approach is that it's very easy to ignore the return value. The compiler doesn't enforce checking it, so you can just forget about it, and then errors slip through undetected until they cause problems later. But the advantage is that it's simple and explicit. There's no hidden control flow. Everything is right there in front of you. The more modern approach is exceptions. Java, Python, C#, JavaScript, Ruby, and many other contemporary languages use exceptions. When something goes wrong, you throw an exception. This causes control flow to immediately jump to the nearest appropriate catch block, or if there isn't one, it propagates up the call stack until something catches it. If nothing catches it, the program terminates. The advantage of exceptions is that they're harder to ignore than return codes. They automatically propagate, and they separate your error handling code from your normal code, which can make the happy path through your function much clearer and easier to read. The disadvantage is that exceptions create hidden control flow. Any function call might throw an exception and jump to some catch block somewhere else in your codebase. This can make code harder to understand and maintain. Also, exception handling has a performance cost, so you shouldn't use exceptions for normal control flow, only for genuinely exceptional situations. The name says it all. Exceptions should be for exceptional circumstances, not for routine error conditions. Then there's the functional programming approach, used in languages like Rust, Haskell, and Scala. Instead of throwing exceptions, functions return a result type or an option type. This is a container that either holds a successful value or holds an error. The type system forces you to check which one you got. You can't access the value without handling the possibility of an error. This gives you compile time safety. No surprises at runtime. The function signature tells you explicitly that it might fail and what kind of error it might return. The disadvantage is that this can be verbose. You have to explicitly unwrap results, check for errors, and handle them. But the advantage is safety and explicitness. Many people consider this a good trade-off. And then there's null. Tony Hoare, who invented the null reference in 1965, has called it his billion-dollar mistake. Null pointer exceptions and null reference exceptions are probably the most common runtime errors in programming. They're everywhere. You have to check for null constantly. And if you forget even once, your program crashes. It's tedious and error-prone. Modern languages are trying to address this with optional types and null safety features. But in many existing codebases, null checking is just a fact of life. Defensive programming involves developing certain habits and mindsets. You assume nothing. You verify everything. You check your inputs. You check your outputs. You verify that preconditions are met before you proceed with an operation. Many programmers use assertions for this, especially in debug builds. Assertions check that certain conditions are true, and if they're not, the program immediately stops. This helps catch bugs early, during development and testing, rather than letting them slip through to production, where they'll cause much bigger problems. However, in production release builds, assertions are often disabled for performance reasons. When you're handling thousands or millions of requests per second, every check takes time. Every validation adds latency. You have to balance safety against performance. Different domains make different choices here. Medical software prioritizes safety above almost everything else. Financial software prioritizes accuracy. Video games might prioritize frame rate and responsiveness. There's no universal right answer. It depends on your requirements, your constraints, and your priorities. Let me tell you another joke. Why do programmers hate nature? It has too many bugs. That's a pun, you see. Bugs meaning insects, but also software defects. I'll admit, these jokes aren't getting any better as we go along. But consistency is important, even in humor. Or perhaps especially in humor. Error messages deserve their own discussion because they're far more important than many developers realize. Error messages are part of your user interface. They're part of the user experience. And yet, how many times have you seen error messages that are completely useless? Error 400. Invalid input. An error occurred. These messages tell the user nothing. They don't explain what went wrong. They don't suggest how to fix it. They just announce that something bad happened. This is frustrating for users. It makes them feel helpless and confused, neither of which is a good feeling to associate with your software. A good error message is specific. It tells the user exactly what went wrong. Instead of invalid input, say email address must contain and its symbol. Instead of file not found, say could not find config.txt in the application directory. Instead of network error, say could not connect to the server. Please check your internet connection and try again. See the difference? These messages give the user information they can actually use. They're actionable. The user knows what to check, what to fix, what to try next. And please, for the love of all that is good in programming, do not show technical error messages to end users. Stack traces are not user-friendly. Internal variable names mean nothing to someone who isn't a developer. Exception class names are incomprehensible jargon to regular people. Save the technical details for your logs, which brings me to my next point. Now we come to code organization and structure. This is one of those topics that sounds simple at first, but becomes increasingly important as projects grow larger and more complex. When you're working on a small script, maybe 100 lines of code, organization doesn't matter much. You can put everything in one file, name your functions whatever you want, and still understand what's going on. But as soon as your project grows beyond a few hundred lines, and especially when multiple people start working on it, organization becomes critical. I like to think of code organization as being similar to organizing a house. If you live alone in a studio apartment, you can leave your things wherever you want. You know where everything is. It's your space. But if you live with roommates, or if you have a larger house with multiple rooms, you need organization. The kitchen stuff goes in the kitchen. The bathroom stuff goes in the bathroom. Everyone agrees on where things belong, and everyone can find what they need. Code is the same way. You need agreed-upon places for things, and you need everyone on the team to follow the same organizational principles. Let me share a small joke with you. Why do programmers always mix up Christmas and Halloween? Because October 31st equals December 25. Oh, I've told this joke before, haven't I? Earlier in the lecture. Well, that's what happens in long presentations. You start repeating yourself. My apologies. The joke is about number systems, as you probably remember. Octal 31 equals decimal 25. It's a bit of wordplay with abbreviations. October for October and octal. Dec for December and decimal. Not terribly funny, but it's the kind of joke programmers tell each other at conferences. So let's talk about file organization first. How should you organize your source code files? Well, That depends somewhat on the language you're using and the conventions of that language's community. But there are some general principles that apply across most languages. First, related code should be grouped together. If you have a bunch of functions that all deal with user authentication, they should probably be in a file called something like authentication or user management. If you have functions that handle database operations, they should be in a database-related file. This seems obvious, but you'd be surprised how many projects just throw everything into one massive file until it becomes completely unmaintainable. Second, separate different concerns into different files or modules. This is related to the single responsibility principle we discussed earlier with functions, but applied at a larger scale. Your user interface code should be separate from your business logic. Your business logic should be separate from your data access code. This separation makes it easier to change one part of the system without affecting others. It also makes it easier to test individual components in isolation. Most modern programming languages have some concept of modules or packages or namespaces. These are ways of organizing code into logical groups. In Python, you have modules and packages. In Java, you have packages. In C#, you have namespaces. In JavaScript, you have modules. The specific mechanism varies, but the concept is the same. You're creating a hierarchical organization of your code, grouping related things together and separating unrelated things. A common pattern that you'll see in many projects is to organize code by layers. You might have a presentation layer that handles the user interface, a business logic layer that contains your core application logic, and a data access layer that handles database operations. Each layer only talks to the layer directly below it. The presentation layer calls the business logic layer. The business logic layer calls the data access layer. This creates a clear separation of concerns and makes the architecture easier to understand. However, there's another school of thought that suggests organizing code by features rather than by layers. Instead of having all your user interface code in one place, all your business logic in another, and all your data access in a third place, you group everything related to a particular feature together. So you might have a user registration module that contains the UI, the business logic, and the data access for user registration, all in one place. Then you have a separate shopping cart module with its UI, logic, and data access. The advantage of this approach is that all the code for a feature is located together, which can make it easier to work on that feature. The disadvantage is that you might have more duplication of infrastructure code across features. Which approach is better? Well, that's a matter of debate. Different teams prefer different approaches. Different types of applications work better with different organizational strategies. Large enterprise applications often use layered architecture. Microservices often use feature-based organization. There's no universal right answer, which is frustrating if you're looking for definitive guidance. But that's software development for you. Almost everything is contextual. Let's talk about naming conventions for files and directories. This might seem like a trivial concern, but it's not. When you have hundreds or thousands of files in a project, consistent naming becomes very important for being able to find things quickly. Some projects use lowercase names with underscores. Some use lowercase with hyphens. Some use camel case. Some use Pascal case. Again, different languages have different conventions. Python typically uses lowercase with underscores. Java typically uses Pascal case for class files. JavaScript is a bit of a mess with no clear consensus. The important thing is to be consistent within your project. Pick a convention and stick to it. Document it if necessary. Make sure everyone on the team follows it. File names should be descriptive but not excessively long. If you have a file called User Authentication Service Implementation, that's probably too long. Just User Authentication or Auth Service would be sufficient. On the other hand, names like utils or helpers or miscellaneous are usually too vague. What kind of utilities? What kind of helpers? These generic names tend to become dumping grounds for random code that doesn't fit anywhere else. Directory structure is equally important. A flat directory structure where all files are in the root directory becomes unmanageable very quickly. You need subdirectories. But how should you organize them? This goes back to the layered versus feature-based question we discussed earlier. In a layered architecture, you might have directories called views, models, and controllers. In a feature-based architecture, you might have directories called user management, product catalog, and shopping cart. Many projects also have standard directories for certain types of files. A test directory for test files. A docs directory for documentation. A config directory for configuration files. A scripts directory for utility scripts. These are conventions that many developers expect to see, so following them makes your project more approachable to new team members. Now let's discuss code structure within files. Even within a single file, organization matters. There are conventional orders for things that make code easier to read and understand. In most languages, imports or includes come at the top of the file. Then constants and global variables, if you have any, though global variables should be used sparingly. Then class definitions, if you're using an object-oriented language. Then function definitions. Then the main execution code, if applicable. Within a class, there's also a conventional order. Public methods usually come before private methods. The most important, most frequently used methods usually come near the top. Constructor and initialization methods typically come first. Then your main public interface methods. Then helper methods and utilities. Then private implementation details at the bottom. This organization means that someone reading your class encounters the most important information first and can stop reading when they've seen enough to understand what they need. Comments within code should be organized too. A comment should come immediately before the code it describes, not after it. If you have a long comment explaining a complex section of code, it should appear at the beginning of that section, not scattered throughout it. File-level comments, if you have them, should be at the very top of the file, explaining what the file contains and perhaps some high-level information about how to use it. Some teams use special comment markers for things like to-do items or feaksome notes. These are useful because they can be searched for. If you search your entire codebase for to-do, you can find all the places where someone marked something as needing attention later. However, to-dos can also become a form of technical debt. It's easy to add a to-do comment with the intention of fixing it later, and then never actually getting around to it. Years later, someone finds a to-do from 2015 and has no idea what it was referring to or whether it's still relevant. Let's talk about the concept of coupling and cohesion. These are fundamental principles in software design. Cohesion refers to how closely related the contents of a module are to each other. High cohesion is good. It means that everything in the module belongs together and serves a common purpose. Low cohesion is bad. It means you've thrown unrelated things together, and the module lacks focus. Coupling refers to how much different modules depend on each other. Low coupling is good. It means modules are independent and can be changed without affecting other modules. High coupling is bad. It means modules are tightly intertwined, and changing one requires changing others. The goal is to maximize cohesion within modules and minimize coupling between modules. This is sometimes called high cohesion, low coupling, and it's been a principle of good software design for decades. When you achieve this, your code becomes much easier to maintain. You can understand one module without needing to understand all the others. You can change one module without breaking others. You can test one module in isolation. However, achieving low coupling can be challenging. Sometimes modules genuinely need to interact. Sometimes they need to share data. Sometimes they need to coordinate their behavior. The trick is to manage these dependencies carefully. Use well-defined interfaces. Minimize the surface area of interaction. Pass data explicitly rather than sharing global state. These practices help keep coupling under control. Dependency injection is a technique that helps reduce coupling. Instead of a class creating its own dependencies directly, you pass them in from the outside, usually through the constructor. This makes the dependencies explicit and makes it easier to substitute different implementations, which is particularly useful for testing. You can inject mock objects during testing instead of real dependencies, allowing you to test one component in isolation. Let me tell you another joke. What's the object-oriented way to become wealthy? Inheritance. That's a pun on inheritance, meaning both receiving money from relatives and the programming concept of class inheritance. Object-oriented programming humor. These jokes really don't improve with repetition, do they? But we're maintaining consistency, which is itself a form of organization. Configuration management is another aspect of code organization that deserves attention. Hard-coded values scattered throughout your code are a maintenance nightmare. Port numbers, timeout values, file paths, API keys, database connection strings. These should not be embedded in your source code. They should be externalized into configuration files. This gives you several benefits. First, you can change configuration without recompiling or redeploying your code. Second, you can have different configurations for different environments. Your development environment uses a local database, your staging environment uses a test database, and your production environment uses the real database. But it's all the same code, with different configuration. Third, you can keep sensitive information like passwords and API keys out of your source code repository, which is a security best practice. There are many approaches to configuration. Configuration files and formats like JSON, YAML, XML, or INI files. Environment variables. Command line arguments. Configuration databases. Each has its place. The important thing is to have a consistent approach within your project. Documentation also needs to be organized. Where does documentation live? Some documentation should be in comments within the code itself. API documentation, for example, often lives in special comments right next to the coded documents, and tools can extract these comments to generate formatted documentation. This is how Javadoc works in Java, or how docstrings work in Python. Other documentation lives in separate files. A README file in your project root is nearly universal. It explains what the project is, how to install it, how to use it, and maybe some basic examples. Many projects also have additional documentation files or even entire documentation websites. The key is that this documentation should be version controlled alongside your code, so it stays in sync as the code changes. Architecture documentation is important for larger projects. This explains the overall structure of the system, the major components, how they interact, and the key design decisions that were made. This kind of documentation helps new team members understand the system quickly. It also serves as a historical record. When someone looks at the code in 5 years and wonders why it was designed this way, the architecture documentation should explain the reasoning. Code organization is not something you do once and then forget about. It's an ongoing process. As the project grows and evolves, the organization needs to evolve too. Modules that made sense when the project was small might need to be split up as they grow. Code that was scattered across multiple places might need to be consolidated. Files that have grown too large might need to be broken up. This is refactoring at the architectural level, and it's a normal part of maintaining a healthy code base. However, reorganizing code is risky. Moving files around, renaming things, restructuring modules, these changes can break things if you're not careful. This is where good version control becomes essential. You need to be able to try a reorganization, and if it doesn't work out, you need to be able to revert it cleanly. You also need good tests to verify that your reorganization didn't break any functionality. This is one of the many reasons why testing is so important, which we'll discuss in more detail in a later section. The organization of your code sends a message about the quality of your project. Well-organized code suggests that someone cares about this project, that someone is maintaining it, that it's being treated professionally. Disorganized code suggests the opposite. It suggests neglect, technical debt, and potential problems. Whether this impression is fair or not, it's the impression that people get. And in many cases, that impression is accurate. Projects that are well organized tend to be better maintained in other ways too. Projects that are disorganized tend to have problems in other areas as well. Organization is often a leading indicator of overall code quality. We now arrive at testing and test-driven development. Testing is one of those topics that everyone agrees is important, but that many people still don't do consistently or thoroughly. It's like exercise or eating vegetables. Everyone knows they should do it, but it's easy to skip when you're busy or when deadlines are looming. And just like with exercise, the benefits of testing aren't immediately obvious. You don't see the payoff right away. It's a long-term investment that pays dividends over time. So what is testing? In the simplest terms, testing means verifying that your code does what you think it does. You write some code, and then you write additional code to check that the first code works correctly. This seems redundant, doesn't it? If you just wrote the code, why would you need to check it? Well, because humans make mistakes. We're fallible. We misunderstand requirements. We overlook edge cases. We make logical errors. We have incorrect assumptions. Testing helps catch these problems before they reach production, before they affect real users, before they cause real damage. There are many different types of testing, and it can be somewhat overwhelming when you first encounter all the terminology. Unit tests, integration tests, system tests, acceptance tests, regression tests, smoke tests, performance tests, security tests, usability tests. The list goes on and on. Each type serves a different purpose and operates at a different level of the system. Let me try to break this down in a systematic way, though I apologize in advance if this becomes rather lengthy. Thoroughness is important with this topic. Let's start with unit tests. Unit tests are the foundation of most testing strategies. A unit test tests a single unit of code in isolation. What's a unit? Usually it's a single function or method, though sometimes it might be a small group of closely related functions. The key word here is isolation. You're testing this one piece of code by itself, without involving any other parts of the system. If the function depends on other things, like a database or external services, you replace those dependencies with test doubles, mock objects, stubs, fakes. These are simplified versions that you control completely in your test. Why test in isolation? Because if a test fails, you want to know exactly what's wrong. If your test involves 10 different functions and it fails, which function has the bug? You don't know without further investigation. But if your test only involves one function and it fails, you know exactly where to look. This makes debugging much faster and much less frustrating. Unit tests should be fast. Very fast. Each individual test should run in milliseconds. When you have thousands of unit tests, and you will have thousands if you're testing a large system properly, they need to be fast so you can run them frequently. You should be able to run your entire unit test suite in a few seconds or maybe a minute or two at most. If it takes longer than that, people won't run the tests as often as they should, and the tests lose much of their value. Unit tests should also be independent. Each test should be able to run by itself without depending on other tests running first. Tests should not share state. They should not depend on a particular order of execution. This is important because test frameworks often run tests in parallel to speed things up, and they might run tests in different orders on different runs. If your tests depend on each other or on running in a specific order, they'll fail intermittently, and intermittent test failures are incredibly frustrating to debug. Let me tell you a joke. Why did the developer go broke? Because he used up all his cache. That's spelled C-A-C-H-E, like computer cache memory, but it sounds like cash, as in money. A homophone pun. These jokes really are scraping the bottom of the barrel, aren't they? But we persist. Consistency. Dedication. Commitment to mediocre humor. Now, integration tests operate at a higher level than unit tests. While unit tests verify individual components in isolation, integration tests verify that different components work together correctly. You're testing the interactions between parts of your system. Does your business logic layer correctly call your data access layer? Does your API correctly parse requests and route them to the right handlers? These are the kinds of questions integration tests answer. Integration tests are slower than unit tests because they involve more of your system. They might hit a real database, though often a test database rather than your production database. They might make real network calls, though usually to test services rather than production services. They're more complex to set up and more brittle than unit tests. If multiple things are involved, there are more things that can go wrong, more ways the test can fail. The trade-off is that integration tests catch different kinds of bugs than unit tests. You might have two components that each work perfectly in isolation, passing all their unit tests, but when you connect them together, they don't work because they have incompatible assumptions about how to communicate. Maybe one expects data in a certain format, and the other provides it in a different format. Unit tests won't catch this but integration tests will. System tests, sometimes called end-to-end tests, go even further. They test your entire system as a whole, from the user interface all the way through to the database and any external services. These tests simulate real user scenarios. A user logs in, searches for a product, adds it to their cart, and completes checkout. The test exercises every layer of your application, every component, every integration point. System tests are valuable because they verify that the entire system works together as intended, but they're also expensive. They're slow to run because they involve so much of the system. They're difficult to write and maintain because they depend on so many things being set up correctly. They're fragile because a change anywhere in the system can break them. And when they fail, it can be difficult to determine what actually went wrong because so many components are involved. This leads to what's often called the testing pyramid. At the base of the pyramid, you have lots of unit tests. These are fast, cheap, and easy to maintain, so you should have many of them. In the middle, you have fewer integration tests. These are slower and more complex, so you have fewer of them than unit tests, but they're still important. At the top, you have even fewer system tests. These are the slowest and most expensive, so you only write them for the most critical user scenarios. The exact ratio varies depending on who you ask, but a common guideline is something like 70% unit tests, 20% integration tests, and 10% system tests. These aren't hard rules, just guidelines. Different applications might need different proportions. A simple command line utility might need mostly unit tests and very few integration tests. A complex web application with many services might need more integration and system tests. Test-driven development, often abbreviated as TDD, takes testing a step further. Instead of writing tests after you write your code, you write tests before you write your code. The process goes like this. First, you write a test for a piece of functionality that doesn't exist yet. You run the test, and of course it fails, because you haven't written the code yet. Then you write just enough code to make the test pass. You run the test again, and if it passes, you move on. If it doesn't pass, you fix your code and try again. Once the test passes, you refactor your code to clean it up, making sure the test still passes. Then you repeat the cycle with the next piece of functionality. This red-green refactor cycle, as it's often called, has some interesting properties. It forces you to think about what you want your code to do before you write it. It ensures that every piece of code you write is testable, because you're writing the test first. It gives you confidence that your code works, because you have a test proving it. And it prevents over-engineering, because you only write enough code to make the test pass, nothing more. However, TDD is not without its critics. Some people find it too rigid and restrictive. Some find that it leads to designing code around tests, rather than around good abstractions. Some find that it doesn't work well for exploratory programming, where you're not sure what you're trying to build yet, and you need to experiment. Like most practices in software development, TDD works very well for some people and some projects, and not as well for others. Let me tell you about code coverage. Code coverage is a metric that measures what percentage of your code is executed by your tests. If you have 100 lines of code, and your tests execute 90 of them, you have 90% code coverage. Many teams track code coverage and set targets, like maintaining at least 80% coverage or not allowing coverage to decrease. Code coverage can be useful, but it's also dangerous if you rely on it too much. High code coverage doesn't necessarily mean your code is well tested. You can execute every line of code without actually verifying that it does the right thing. A test that executes code but doesn't check the results doesn't prove anything. Similarly, low code coverage doesn't necessarily mean your code is poorly tested. Some code might not need testing. Trivial getters and setters, for example, or generated code. The real value of code coverage is in finding gaps. If you look at your code coverage report and see that certain functions or modules have no coverage at all, that's useful information. Those are areas that might need testing. But hitting a specific coverage percentage shouldn't be the goal in itself. Writing good, meaningful tests that actually verify correct behavior should be the goal. Regression testing is another important concept. A regression is when something that used to work stops working. You fix a bug, or you add a new feature, and in the process you accidentally break something else that was working fine before. This happens more often than we'd like to admit. The way to prevent regressions is to have a comprehensive test suite that you run regularly. When you fix a bug, you add a test that verifies the fix. Now, if someone accidentally reintroduces that bug in the future, the test will catch it. Automated testing is crucial for regression prevention. If running your tests is a manual process that someone has to remember to do, it won't happen consistently. Tests need to run automatically. Many teams run their entire test suite every time someone commits code to the repository. This is called continuous integration, and it's become standard practice in modern software development. If someone's change breaks something, you find out immediately, while the change is still fresh in their mind, making it much easier to fix. Test frameworks and tooling have evolved significantly over the years. Every major programming language now has multiple mature testing frameworks. JUnit for Java, PyTest for Python, Jest for JavaScript, and Unit for C#. These frameworks handle the mechanics of running tests, reporting results, and organizing test code. They provide assertions, which are ways to check that values match expectations. They provide setup and teardown hooks for initializing test conditions and cleaning up afterward. They provide ways to organize tests into suites and run subsets of tests. Mocking frameworks help you create test doubles for dependencies. If your code needs to talk to a database, but you don't want your unit test to actually hit a database, a mocking framework lets you create a fake database that responds exactly how you tell it to. This gives you complete control over the test environment and makes tests fast and predictable. Writing good tests is a skill that takes practice. It's not enough to just have tests. You need tests that are clear, maintainable, and actually verify important behavior. A good test has three parts, often called the arrange-act-assert pattern. First, you arrange, setting up the conditions for the test. You create objects, set up test data, configure mocks. Second, you act, executing the code you're testing. You call the function or method you want to verify. Third, you assert, checking that the results match your expectations. You verify that return values are correct, that state changed appropriately, that side effects occurred as expected. Test names are important. A good test name describes what scenario is being tested and what the expected outcome is. Something like test user authentication with valid credentials should succeed is much better than test 1 or test authentication. When a test fails, you want to immediately understand what went wrong just from looking at the test name. This makes debugging faster and makes your test suite serve as documentation for how the system should behave. Tests should be deterministic. A test should either always pass or always fail for a given version of the code. Flaky tests, tests that sometimes pass and sometimes fail without any code changes, are a serious problem. They undermine confidence in your test suite. When tests fail randomly, people start ignoring test failures, assuming it's just a flaky test rather than a real problem. Then real bugs slip through because nobody's paying attention anymore. Common causes of flaky tests include dependencies on external services that might be unavailable, timing-dependent code that behaves differently depending on how fast things run, and tests that depend on shared state or resources where parallel execution can cause conflicts. Fixing flaky tests should be a high priority because they cause so much damage to team productivity and code quality. Performance testing is different from correctness testing. Instead of verifying that your code produces the right results, performance tests verify that it produces results fast enough. Does this database query complete in under 100 milliseconds? Does this API endpoint respond within 2 seconds? Can this service handle 1,000 requests per second? These are the questions performance tests answer. Performance testing often requires different tools and infrastructure than functional testing. You might need to generate realistic load, simulate many concurrent users, measure response times accurately, and identify bottlenecks. This is specialized enough that many teams have dedicated performance testing environments and specialized engineers who focus on it. Security testing is yet another specialized area. Security tests look for vulnerabilities. Can an attacker inject SQL commands through your input fields? Can they access data they shouldn't have access to? Can they cause your system to crash or behave incorrectly? Security testing includes both automated scanning tools that look for known vulnerability patterns and manual penetration testing, where security experts try to break into your system. The reality is that most teams don't do enough testing. It's time-consuming. It's not as immediately gratifying as writing new features. It's often not valued by management who want to see visible progress. But inadequate testing leads to bugs in production, which leads to incidents, which leads to emergency fixes, which leads to stress and poor quality of life for developers. It's much better to invest in testing up front than to pay the price later in production issues and emergency patches. Testing is also about confidence. When you have a good test suite, you can make changes to your code with confidence. You can refactor without fear. You can add features knowing that if you break something, the test will tell you. Without tests, every change is scary. You never know what you might have broken. You're reluctant to improve the code because you might make things worse. This fear of change leads to stagnation and technical debt accumulation. Good testing practices, like good programming practices in general, require discipline and consistency. They require investment. They require team buy-in. They require time. But the return on that investment is enormous. More reliable software, fewer production issues, faster development in the long run, higher quality code, less stress for developers. These benefits are real and substantial, even if they're not always immediately visible. Now we turn to version control, and specifically Git best practices. Version control is one of those technologies that seems intimidating when you first encounter it. But once you understand it, you wonder how anyone ever programmed without it. And indeed, people did program without version control for many years, and it was rather chaotic. Code was lost. Changes were overwritten. Collaboration was painful. We've come a long way since those dark days. Version control is fundamentally about tracking changes to files over time. Every time you make a change to your code and commit it to version control, you're creating a snapshot of your project at that moment. You can go back to any previous snapshot at any time. You can see what changed between snapshots. You can see who made changes and when. You can have multiple people working on the same codebase simultaneously without stepping on each other's toes. Well, without stepping on each other's toes too much anyway. Conflicts still happen, but version control gives you tools to resolve them. Git has become the dominant version control system in modern software development. It wasn't always this way. In my early career, we used CVS, then Subversion, then a period where different teams used different systems. But Git has essentially one. Almost every open source project uses Git. Almost every company uses Git. If you learn version control, you learn Git. There are other systems out there, Mercurial and Perforce and others, but Git is what you'll encounter most of the time. Git is a distributed version control system, which means every developer has a complete copy of the entire repository history on their local machine. This is different from older centralized systems, where there was one authoritative server, and everyone had to connect to it to do anything. With Git, you can work offline. You can commit changes locally. You can view history locally. You only need to connect to a server when you want to share your changes with others or retrieve their changes. Let me tell you a joke before we get too deep into the technical details. Why did the developer quit his job? He didn't get a raise. That's spelled R-R-A-Y-S, like the data structure, but it sounds like a raise, as in a salary increase. These programming puns really are quite terrible, aren't they? But we've established a pattern, and breaking patterns would be inconsistent. Consistency is important, even in terrible jokes. So let's talk about commits. A commit is a saved snapshot of your project. When you commit changes in Git, you're saying, this is a meaningful point that I want to be able to return to later. But what makes a good commit? This is actually more nuanced than it might seem. First, commit should be atomic. This means a commit should represent one logical change. If you're fixing a bug, the commit should contain the bug fix and nothing else. If you're adding a feature, the commit should contain that feature. Don't mix unrelated changes in the same commit. Why does this matter? Because later, when you're looking through the history, try to understand when something changed or why. Atomic commits make that much easier. You can see exactly what changed for each logical modification. Second, commit should be complete. Don't commit half-finished work. Well, there are exceptions to this, but generally speaking, the code at each commit should be in a working state. It should compile. It should pass tests. This is important because you might need to check out that commit later, perhaps to track down when a bug was introduced. And if the code doesn't even work at that point, you'll have a hard time. Third, commit messages matter. A good commit message explains what changed and why. The what should be apparent from looking at the code changes, but the why is often not obvious. Why did you make this change? What problem were you solving? What requirement were you addressing? Future you, looking at this commit 6 months from now, will want to know. Your colleagues, trying to understand the system, will want to know. A commit message like fix bug is useless. Which bug? How did you fix it? Why did you fix it this way rather than some other way? A conventional format for commit messages is to have a short summary line, no more than 50 or 70 characters, that describes the change at a high level. Then a blank line. Then a more detailed explanation if needed. The detailed explanation can be multiple paragraphs if necessary. It can reference issue tracker numbers. It can explain context and reasoning. Some teams follow very specific formats for commit messages, even using conventions like starting messages with keywords like feat for features or fix for bug fixes. These conventions make it easier to automatically generate change logs and release notes. Branching is one of Git's most powerful features, but it's also one that causes confusion for people new to version control. A branch is essentially a parallel line of development. The main branch, often called main or master, represents the stable, production-ready code. When you want to work on something new, you create a branch. You make your changes on that branch. When you're done, you merge the branch back into main. This keeps experimental or in progress work separate from stable code. Different teams have different branching strategies, and there are several popular models. Git Flow is one of the older, more complex branching strategies. It involves multiple types of branches, feature branches, release branches, hotfix branches, and so on. It's quite structured and formal, which works well for some teams, but feels like overkill for others. GitHub Flow is simpler. You have the main branch, which is always deployable. When you want to work on something, you create a feature branch. You make your changes, you open a pull request, someone reviews your code, and then you merge to main and deploy. This works well for teams that deploy frequently, which is increasingly common. Trunk-based development is even simpler. Everyone commits to the main branch, or to very short-lived branches that get merged quickly. The idea is to integrate continuously and avoid long-lived branches that diverge significantly from main. This requires good automated testing because you're committing to the main branch frequently, and you need confidence that you're not breaking things. Which approach is best? As usual in software development, it depends. Larger teams, with more formal release processes, might prefer Git Flow. Smaller teams that deploy continuously might prefer GitHub Flow or trunk-based development. The important thing is that everyone on the team follows the same strategy and understands it. Pull requests, also called merge requests in some systems, are a code review mechanism. Instead of directly merging your branch into main, you open a pull request. This is a request for other team members to review your changes before they're merged. They can leave comments, suggest improvements, ask questions. This serves multiple purposes. It catches bugs before they reach the main branch. It spreads knowledge about the codebase across the team. It maintains code quality. It's an opportunity for mentoring junior developers. However, pull requests can also become bottlenecks if not managed well. If reviews take days or weeks, development slows down. If reviewers are too nitpicky, focusing on minor style issues rather than substantive problems, developers get frustrated. If reviews are too superficial, just rubber stamping everything, they lose their value. Good code review is a skill that takes practice, both for reviewers and for people submitting code for review. Merge conflicts are an inevitable part of working with version control when multiple people are editing the same codebase. A merge conflict occurs when Git can't automatically determine how to combine changes from different branches. Maybe two people edited the same line of code in different ways. Maybe one person added code where another person deleted code. Git will mark these conflicts and require a human to resolve them. Resolving merge conflicts can be frustrating, especially complex ones involving many files. The key is to understand what each side of the conflict represents and decide what the final code should look like. Sometimes you want the changes from one branch. Sometimes you want the changes from the other branch. Sometimes you need to combine elements from both. Sometimes neither is quite right, and you need to write something new that incorporates both sets of changes appropriately. The best way to minimize merge conflicts is to merge frequently. Long-lived branches that diverge significantly from main are much more likely to have conflicts. If you merge your feature branch regularly, pulling in changes from main, you deal with conflicts in small increments rather than all at once at the end. This is one reason why trunk-based development, with its very short-lived branches, has become popular. Let me share another joke with you. What do you call a programmer who doesn't comment their code? Unemployed. Well, that's not really true, is it? Plenty of programmers don't comment their code and remain employed. But the joke is suggesting they should be unemployed. That good practices, like commenting, should be job requirements. It's aspirational humor, or perhaps wishful thinking. Git has many commands, and learning them all can feel overwhelming. The basic workflow is actually quite simple, though. You clone a repository to get a local copy. You create a branch for your work. You make changes to files. You stage those changes with git add. You commit the staged changes with git commit. You push your commits to a remote server with git push. You pull changes from others with git pull. That's the core workflow that covers 90% of daily usage. But Git has many more commands for more specialized situations. Git log shows you commit history. Git diff shows you what changed. Git blame shows you who last modified each line of a file, which sounds accusatory but is actually useful for understanding why code is the way it is. Git bisect helps you find which commit introduced a bug by doing a binary search through history. Git rebase rewrites commit history, which is powerful but also dangerous if you don't understand what you're doing. There's a saying in the Git community, don't rebase public history. What this means is that you shouldn't rewrite commits that you've already shared with others. Rebasing creates new commits, even though they might have the same changes. If others have based their work on your original commits, and then you rewrite those commits, you've created a confusing situation that's difficult to resolve. Rebase is safe for cleaning up your own local commits before you share them, but once you've pushed commits, leave them alone. Git hooks are another powerful feature that many people don't know about. Hooks are scripts that run automatically at certain points in the Git workflow. You can have a pre-commit hook that runs your code linter before allowing a commit. You can have a pre-push hook that runs your test suite before allowing a push. You can have post-merge hooks that do cleanup or send notifications. Hooks let you automate checks and enforce policies. The git ignore file is important for keeping unnecessary files out of version control. You don't want to commit compiled binaries or temporary files or IDE-specific configuration files or log files. These are generated files that don't need to be in version control and would just clutter up your repository. A good git ignore file, configured appropriately for your project and language, keeps these out automatically. Platforms like GitHub, GitLab, and Bitbucket have built entire ecosystems around Git. They provide web-based interfaces for browsing repositories, viewing diffs, managing pull requests, and discussing code. They provide issue tracking integrated with your repository. They provide continuous integration systems that automatically build and test your code when you push commits. They provide ways to deploy code directly from branches or tags. These platforms have become central to modern software development workflows. Open source development in particular has been revolutionized by these platforms. Anyone can fork a project, make changes, and submit a pull request. Maintainers can review and merge contributions from people all over the world. The entire history of a project is public and searchable. Issues and discussions are archived and linkable. This transparency and ease of contribution has led to an explosion of open-source software. However, version control is not just for code. You can and should version control other things too. Configuration files, documentation, Database migration scripts. Infrastructure as code definitions. Anything text-based that changes over time benefits from version control. This gives you history, the ability to roll back changes, and the ability to collaborate with others. Some teams even version control things you might not expect. Design documents, architecture diagrams, meeting notes. By keeping these in version control alongside the code, you ensure they stay synchronized. When you look at a particular commit or a particular release, you can see not just the code at that point, but also the documentation and requirements that were current at that time. This historical context can be invaluable. Git tags are used to mark specific commits as important. Typically, tags are used for releases. When you release version 2.3.5 of your software, you create a tag called version 2.3.5 pointing to the commit that represents that release. Now you can easily check out that exact version later. You can see what code was in that release. You can create a branch from that tag if you need to make a hotfix to that version. Tags are lightweight markers, but they serve an important role in release management. Learning Git takes time and practice. Everyone who uses Git has, at some point, gotten themselves into a confusing situation. They've accidentally committed to the wrong branch. They've created a merge conflict they don't know how to resolve. They've accidentally deleted commits. They've pushed something they shouldn't have pushed. These mistakes are part of the learning process. The good news is that Git is remarkably resilient. It's very difficult to actually lose data permanently. Almost everything can be recovered if you know the right commands, though you might need to consult Stack Overflow or ask a more experienced colleague for help. The key to using Git effectively is to develop good habits. Commit frequently. Write good commit messages. Keep commits atomic. Merge or rebase regularly to stay synchronized with your team. Review your changes before committing. Pull before you push. These habits, once established, become second nature, and version control becomes a natural part of your development workflow rather than something you have to think about consciously. Version control, and Git specifically, is one of those fundamental tools that every professional developer needs to know. It's as basic as knowing how to use a text editor or a compiler. You can't really work on any serious software project without it. The good news is that while Git has a reputation for being complex, and it can be in advanced scenarios, the day-to-day usage is actually quite straightforward once you understand the basic concepts. And the benefits it provides in terms of safety, collaboration, and maintainability are absolutely worth the learning investment. We now come to the topic of performance and optimization. This is an area where developers often make mistakes, usually by doing too much optimization too early, or by optimizing the wrong things. There's a famous quote by Donald Knuth that I mentioned briefly earlier, and it's worth repeating in full. Premature optimization is the root of all evil. Well, the full quote actually says the root of all evil in programming, and there's more to it, but that's the part everyone remembers. What Knuth meant is that optimizing code before you know whether optimization is needed is usually a waste of time at best, and actively harmful at worst. Optimized code is often more complex, harder to read, harder to maintain. If you're making your code more complex to optimize something that isn't actually a bottleneck, you're just making your code base worse for no benefit. This is a mistake I see students make regularly, and I made it myself when I was younger. You write some code, and then you think, how can I make this faster? And you spend hours making it faster, and in the end, that code runs for 10 milliseconds instead of 12 milliseconds, but it runs once when the program starts. So the optimization saved 2 milliseconds total, and the code is now twice as hard to understand. The correct approach to optimization is to first make your code work correctly. Make it clear. Make it maintainable. Then, and only then, if you have evidence that performance is a problem, you measure where the actual bottlenecks are, and you optimize those specific parts. This is often called the make it work, make it right, make it fast approach. First priority is correctness. Second priority is good design and maintainability. Third priority, only if needed, is performance. How do you know if you need to optimize? You measure. You profile your code. Profiling tools will tell you exactly where your program is spending its time. What functions are being called most frequently? What operations are taking the longest? Where are the bottlenecks? Without this data, you're just guessing, and humans are notoriously bad at guessing where performance problems are. We have intuitions about what should be slow, but those intuitions are often wrong. I've seen developers spend days optimizing a database query that runs once per hour, while ignoring a loop that runs 10,000 times per second. The query optimization saved 50 milliseconds per hour. The loop, even though each iteration was fast, was the actual bottleneck because of how frequently it ran. But the query seemed more obvious, more visible, so that's what got attention. This is why measurement is crucial. Let me tell you a joke. Why do Java developers wear glasses? Because they can't see sharp. That's C# as in the programming language C#, but it sounds like can't see sharp, as in poor vision. These jokes really don't improve, do they? But we're committed to the format at this point. 10 sections in, might as well maintain consistency. So let's discuss different types of performance problems and how to address them. One common issue is algorithmic complexity. This is often taught in computer science courses using big O notation. An algorithm that's O of n is linear. If you double the input size, it takes twice as long. An algorithm that's O of n squared is quadratic. If you double the input size, it takes 4 times as long. An algorithm that's O of log n is logarithmic. Doubling the input size barely increases the time at all. The difference between these complexity classes becomes dramatic with large inputs. If you're processing 10 items, it doesn't matter much whether your algorithm is O of n or O of n squared. But if you're processing 1,000,000 items, the difference between a linear algorithm and a quadratic algorithm is the difference between seconds and days. Sometimes the best optimization is to use a better algorithm rather than trying to make your existing algorithm faster. For example, if you're searching for an item in an unsorted list, you have to check each item one by one, which is O of n. But if you sort the list first, then you can use binary search, which is O of log n. The sorting itself takes time, of course, O of n log n for good sorting algorithms, but if you're going to search multiple times, the upfront cost of sorting pays off. This is the kind of algorithmic thinking that can lead to major performance improvements. Data structures matter too. Different data structures have different performance characteristics for different operations. Arrays are great for random access, but expensive for insertions in the middle. Linked lists are great for insertions, but terrible for random access. Hash tables are great for lookups, but use more memory. Trees provide balanced performance for many operations. Understanding these trade-offs and choosing the right data structure for your use case is often more important than micro-optimizations. Caching is another powerful optimization technique. If you're computing the same thing multiple times, compute it once and save the result. If you're fetching the same data repeatedly, fetch it once and cache it. The trick with caching is cache invalidation, which, as the saying goes, is one of the 2 hard problems in computer science. When does cached data become stale? When do you need to invalidate it and recompute or refetch? Get this wrong, and you have subtle bugs where users see old data instead of current data. There are different levels of caching. You can cache in memory within your application. You can cache in a dedicated caching system like Redis or Memcached. You can cache at the database level. You can cache at the HTTP level with CDNs. Each level has different characteristics, different benefits, different complexities. Often, you use multiple levels of caching together, which makes invalidation even more complex. Database optimization is its own specialized area. Databases can be major bottlenecks in web applications. Queries that scan entire tables instead of using indexes. N+1 query problems, where you make hundreds of separate queries instead of using joins. Missing indexes on columns you're filtering or sorting by. These are common issues that can have dramatic performance impacts. Query optimization often involves understanding how the database executes your queries. Most databases can show you query execution plans, which explain what the database is actually doing step by step. Are you doing full table scans? Are your indexes being used? Are you sorting in memory? These plans can look intimidating at first, but learning to read them is a valuable skill. Network performance is another consideration, especially for distributed systems. Every network call has latency. Even on a fast network, There's overhead in establishing connections, transmitting data, waiting for responses. If your application makes many sequential network calls, those latencies add up. Sometimes you can parallelize, making multiple calls simultaneously. Sometimes you can batch, sending multiple requests together. Sometimes you can reduce the number of calls by sending more data per call. Memory usage matters too. Using more memory isn't always a problem. Memory is relatively cheap these days, but eventually you hit limits. If your application uses more memory than physically available, the operating system starts swapping to disk, and performance falls off a cliff. Garbage collection in managed languages can also be affected by memory usage patterns. Allocating many small objects creates work for the garbage collector. Memory leaks, where you accidentally keep references to objects you no longer need, gradually consume memory until your application crashes. Some optimizations are about reducing work. If you can avoid doing something, that's faster than doing it efficiently. Do you really need to process all that data? Can you filter earlier in the pipeline? Do you need to compute that value every time? Or can you compute it once when it changes? Sometimes the best optimization is to do less. Lazy evaluation is a technique where you delay computation until the result is actually needed. Maybe you prepare a large dataset, but the user only looks at the first 10 results. Why process the entire dataset if they're only going to use 10% of it? Lazy evaluation lets you do the minimum necessary work. However, it can make code harder to understand because it's not immediately clear when things actually happen. Multi-threading and parallelism can provide performance improvements on modern multi-core processors, but they also introduce complexity. Concurrent code is harder to write, harder to test, harder to debug. Race conditions, deadlocks, and other concurrency bugs are notoriously difficult to track down. Before reaching for multi-threading, make sure you actually need it. If your bottleneck is I/O rather than CPU, multi-threading might not help much. If your bottleneck is a single operation that can't be parallelized, adding more threads won't make it faster. Code-level micro-optimizations are usually the last thing you should worry about. Things like whether to use a for loop or a while loop, whether to increment a variable with ++ or equals +1, whether to use string concatenation or a string builder. Modern compilers are very good at optimizing these kinds of things. The performance difference is usually negligible. The readability difference might be significant. In almost all cases, you should write the code that's clearest and most maintainable, and trust the compiler to optimize the low-level details. There are exceptions, of course. If you're writing a game engine or a high-frequency trading system or embedded software, micro-optimizations might matter. If you're in a tight loop that runs billions of times, small optimizations can add up. But these are specialized cases. For most business applications, for most web services, for most data processing, algorithmic improvements and architectural changes will give you much more benefit than micro-optimizations. Let me tell you another joke. Why did the programmer quit his job at the farm? He couldn't find the right code. That's a pun on code and cows. Or, actually, I'm not sure this joke works at all. Maybe I misremembered it. In any case, we're maintaining our streak of mediocre programmer humor. Performance testing is important if performance actually matters for your application. This means setting up realistic test scenarios, generating realistic load, and measuring response times under those conditions. What's realistic depends on your application. For a website, it might be hundreds or thousands of concurrent users. For a data processing system, it might be processing gigabytes of data. For an API, it might be thousands of requests per second. Load testing tools can simulate this kind of traffic and give you detailed metrics. How many requests per second can your system handle? What's the average response time? What's the 99th percentile response time? That last one is important because averages can be misleading. If most requests take 50 milliseconds, but 1% take 5 seconds, your average might look fine, but 1 in 100 users is having a terrible experience. Performance regressions are when performance gets worse over time. As you add features and make changes, performance can gradually degrade. Small changes that individually don't matter much can add up to significant slowdowns. This is why it's useful to track performance metrics over time and to have automated performance tests that run regularly. If you notice performance degrading, you can investigate what changed recently. Scalability is related to but distinct from performance. Performance is about how fast your system is. Scalability is about how well it handles increased load. A system might perform great with 10 users, but fall apart with 100 users. Or it might work fine with 100 users, but struggle with 10,000. Understanding your system's scalability characteristics and its limits is important for capacity planning. There are two types of scaling: vertical and horizontal. Vertical scaling means making your existing hardware more powerful. More CPU, more RAM, faster disks. This is the simple approach, but it has limits. At some point, you can't get a bigger machine. Horizontal scaling means adding more machines. Instead of one powerful server, you have many less powerful servers working together. This can scale much further, but it requires your application to be designed for it. Not all applications can easily scale horizontally. Databases are often the hardest part to scale. Scaling a single database vertically only gets you so far. Scaling horizontally means either replication, where you have multiple copies of the database, or sharding, where you split the data across multiple databases. Both add significant complexity. Replication means dealing with consistency issues. If you write to one copy, how quickly does that change propagate to the others? Sharding means figuring out how to split your data and how to handle queries that span multiple shards. Cloud computing has made it easier to scale in some ways. You can spin up additional servers on demand. You can scale up during peak times and scale down during quiet times. Autoscaling can do this automatically based on load. But cloud computing hasn't made the fundamental problems of scalability go away. You still need to design your application to scale. You still need to understand your bottlenecks. You still need to test under load. The cost of optimization needs to be considered too. Making something twice as fast might require weeks of development time. Is that worth it? If you're saving your users significant time, maybe yes. If you're saving milliseconds on something that happens rarely, probably no. Performance optimization competes with other priorities like new features, bug fixes, and paying down technical debt. You have to make trade-offs based on what actually provides the most value. Sometimes the best performance optimization is at the product level rather than the technical level. Maybe instead of making a report generate faster, you pre-generate it nightly and serve the cached version. Maybe instead of supporting real-time updates, you batch updates every few minutes. These product-level decisions can sometimes be much easier and cheaper than technical optimizations, though they do require trade-offs in functionality. Documentation of performance characteristics can be valuable. If a particular operation is known to be slow with large datasets, document that. If a particular configuration setting has performance implications, document that. This helps users of your code, whether internal team members or external users, understand what to expect and how to use your system efficiently. Performance optimization is ultimately about making trade-offs. Faster code that's unmaintainable isn't a win. High performance that costs too much to achieve isn't worth it. Optimizing parts of the system that aren't bottlenecks is wasted effort. The art of performance optimization is knowing when to optimize, what to optimize, and how much effort to invest. And that knowledge comes from measurement, from experience, and from keeping the big picture in mind rather than getting lost in the details. We now come to the topic of security best practices. Security is one of those areas of programming that many developers don't think about enough until something goes wrong. And when something goes wrong with security, it goes very wrong indeed. Security breaches make headlines. They cost companies millions of dollars. They damage reputations. They expose sensitive customer data. They result in lawsuits and regulatory fines. Security is not something you can afford to treat as an afterthought. The challenge with security is that you have to get it right every single time, while an attacker only has to find one vulnerability. You have to defend against every possible attack vector, while an attacker only needs to find one weakness. This asymmetry makes security particularly difficult. It's a game where the defenders are at a fundamental disadvantage. But that doesn't mean we shouldn't try. Good security practices can prevent the vast majority of attacks. Let me tell you a joke before we dive deeper into this topic. Why do programmers prefer dark mode? Because light attracts bugs, and security bugs are the worst kind. Wait, I think I've told some variation of this joke before. Several times, actually. My apologies for the repetition. When you give long lectures, these things happen. The joke is about bugs being both software errors and insects, though I suppose I don't need to explain that again. The first principle of security is never trust user input. We discussed this in the error handling section, but it bears repeating in the security context because it's so critical. Every piece of data that comes from outside your system is potentially malicious. Users might not be trying to attack you, but they might make mistakes that create security problems. Or they might be trying to attack you. You can't know which, so you have to treat all external input as untrusted. SQL injection is one of the most common and most dangerous vulnerabilities. It occurs when you construct SQL queries by concatenating strings that include user input. If the user input contains SQL code, that code gets executed. An attacker can use this to read data they shouldn't have access to, modify or delete data, or even take over the entire database server. The solution is to never construct SQL queries through string concatenation. Always use parameterized queries or prepared statements. These separate the SQL code from the data, making injection impossible. Cross-site scripting, usually abbreviated as XSS, is another common vulnerability in web applications. It occurs when you display user-provided content without properly escaping it. If a user submits content that includes JavaScript code, and you display that content to other users, that JavaScript code will execute in their browsers. An attacker can use this to steal session cookies, perform actions on behalf of other users, or redirect them to malicious sites. The solution is to always escape user-provided content before displaying it. Or better yet, use frameworks that escape content by default. Cross-site request forgery, abbreviated as CSRF, is a vulnerability where an attacker tricks a user's browser into making requests to your application. The user is logged into your application, so their browser sends their authentication cookies with the request, and your application thinks it's a legitimate request from that user. The attacker can use this to perform actions on behalf of the user without their knowledge. The solution is to use CSRF tokens, which are random values included in forms that must be submitted with the form data to prove the request came from your application. Authentication is the process of verifying who someone is. Authorization is the process of determining what they're allowed to do. These are related but distinct concepts, and both are critical for security. For authentication, you need to verify that users are who they claim to be. This usually involves passwords, though increasingly we're moving toward multi-factor authentication, which requires something you know like a password plus something you have like a phone or security key. Passwords should never be stored in plain text. If an attacker gains access to your database, they shouldn't be able to read user passwords. Instead, passwords should be hashed using a strong cryptographic hash function designed for password storage. Functions like bcrypt, scrypt, or argon2 are appropriate. These functions are intentionally slow, which makes it impractical for an attacker to try millions of passwords to find the right one. Regular hash functions like SHA-256 are not suitable for password storage because they're too fast. You should also salt passwords before hashing them. A salt is a random value that's combined with the password before hashing. Each user gets a different random salt. This prevents attackers from using precomputed tables of password hashes to crack passwords efficiently. The salt doesn't need to be kept secret, just random and unique per user. It's typically stored alongside the hashed password in your database. Session management is critical for web applications. After a user logs in, you need to remember that they're authenticated as they navigate through your application. This is typically done with session cookies. The cookie contains a session ID, which is a long random value that identifies the session. Your server looks up this session ID to find the associated user. Session IDs must be cryptographically random and long enough that an attacker can't guess them. They should also expire after a reasonable time, and they should be invalidated when the user logs out. Access control is about ensuring that users can only access resources they're authorized to access. This should be enforced on the server side, not just in the user interface. Just because you hide a button in the UI doesn't mean an attacker can't figure out what request that button would have made and make that request directly. Every request that accesses sensitive data or performs sensitive operations needs to check whether the current user is authorized to do that. Encryption is about protecting data from unauthorized access. Data in transit, traveling over networks, should be encrypted using TLS, which is the modern version of SSL. This prevents attackers from eavesdropping on network traffic and reading sensitive information. You should use HTTPS for all web traffic, not just for login pages. Modern browsers are increasingly treating HTTP sites as insecure and warning users about them. Data at rest, stored in databases or on disk, should also be encrypted if it's sensitive. If an attacker gains access to your database backups or your hard drives, they shouldn't be able to read the data. However, encryption at rest is more complex than encryption in transit because you need to manage encryption keys securely. If the keys are stored on the same system as the encrypted data, an attacker who compromises that system might be able to access both the data and the keys. The principle of least privilege says that users and systems should only have the minimum permissions necessary to do their jobs. Don't give everyone administrator access just because it's convenient. Don't run your application with root or system privileges if it doesn't need them. Don't give your database user permission to drop tables if all it needs to do is read and write data. The more permissions something has, the more damage it can do if it's compromised. Defense in depth is the principle of having multiple layers of security. Don't rely on a single security mechanism. If one layer fails, other layers should still provide protection. For example, you might have a firewall that blocks most malicious traffic, plus input validation that rejects malicious input, plus parameterized queries that prevent SQL injection, plus access controls that limit what damage an attacker can do even if they get past everything else. Each layer reduces risk, and together they provide much stronger security than any single layer alone. Security updates and patches are critical. When vulnerabilities are discovered in software you're using, whether it's your operating system, your web server, your database, your programming language, or your libraries, those vulnerabilities need to be patched promptly. Attackers actively scan the internet for systems running vulnerable software. Once a vulnerability is publicly known and a patch is available, you're in a race against attackers to patch your systems before they find and exploit them. Dependency management is related to this. Modern applications use many third-party libraries and frameworks. Each of those dependencies is potential attack surface. If a library you're using has a security vulnerability, your application has that vulnerability too. You need to keep track of your dependencies, monitor for security advisories, and update dependencies when security issues are found. Tools exist to automate this scanning and alert you to known vulnerabilities in your dependencies. Logging and monitoring are important for security. You should log security-relevant events like login attempts, both successful and failed, changes to sensitive data, and access to sensitive resources. These logs help you detect attacks in progress or investigate breaches after they occur. However, be careful not to log sensitive information like passwords or credit card numbers. Logs themselves need to be protected because they might contain valuable information for attackers. Error messages should be informative to legitimate users, but not helpful to attackers. Don't include stack traces or internal system details in error messages shown to users. Don't reveal whether a login failed because the username doesn't exist or because the password was wrong. That information helps attackers enumerate valid usernames. Keep error messages generic like invalid username or password, rather than specific. Regular security testing should be part of your development process. This includes both automated scanning tools that look for common vulnerabilities and manual security reviews, where someone thinks like an attacker and tries to find weaknesses. Penetration testing, where security professionals attempt to break into your system, can find vulnerabilities that automated tools and code reviews miss. These should be done regularly, especially before major releases or after significant changes. Security is not a checkbox that you can tick off once and forget about. It's an ongoing process. New vulnerabilities are discovered all the time. Attackers develop new techniques. Your application changes and might introduce new vulnerabilities. Security requires constant attention and vigilance. It requires keeping up with current threats and best practices. It requires a security mindset where you're always thinking about what could go wrong and how to prevent it. The cost of poor security can be enormous. Beyond the direct financial costs of breach response and potential fines, there's reputational damage that can be hard to recover from. Customers lose trust in companies that don't protect their data adequately. Partners become reluctant to work with you. Regulatory scrutiny increases. In some industries, a major security breach can effectively end a company. This might sound dramatic, but it has happened. On the other hand, good security practices are not that difficult if you build them into your development process from the beginning. They become habits. They become part of how you think about problems. Many security vulnerabilities come from well-known, well-understood mistakes that have well-known solutions. SQL injection, XSS, CSRF, insecure password storage. We've known how to prevent these for decades. Yet they still appear regularly in applications because developers either don't know about them or don't prioritize fixing them. Security training for developers is valuable. Many developers have never received formal training in secure coding practices. They learn to make things work, but not necessarily to make them secure. Organizations that invest in security training for their development teams see measurable improvements in security. Developers who understand common vulnerabilities and how to prevent them will naturally write more secure code. Finally, I want to emphasize that security is everyone's responsibility. It's not just the security team's job, if you even have a security team. Every developer who writes code that handles sensitive data or user input has a responsibility to think about security. Every code reviewer should be looking for security issues. Every tester should be thinking about security test cases. Security needs to be integrated throughout the development process, not bolted on at the end. We haven't finished yet, but I think the next hour's professor is going to beat me if I don't stop now. We'll finish the last part in next lesson. See you soon. Remember to read again those important concepts on your notes.